Hello, I would like to perform a conservation of energy problem where non-conservative forces do act for a calculus-based Physics 1 class. This is from my lecture slides and corresponds to our Chapter 8. So what we have here is a 60.0 kilogram skier with an initial speed of 12.0 meters per second, coasts up a 2.50 meter rise as shown. Find his final speed at the top, given a coefficient of friction of mu k equals 0.0800, which is actually a very approximate sort of common coefficient of kinetic friction for skis on snow. By the way, also notice that if there's one other known we sort of do know here is this 35, and that's degrees, and that I think is the angle of the rise. So let us first write that down, and then the other values that are given, let's write those down. So we can say first that theta is equal to 35 degrees. Secondly, we can say that the mass of the skier, that's m, is 60.0 kilograms. Next, the initial speed is 12 meters per second. So that's v initial, just the magnitude of the velocity, is 12.0 meters per second. And we know we're going to coast up a 2.50 meter rise. So why don't we call that y final? The final height is 2.50 meters. By the way, let's just assume we have 3 significant digits for every one of these numbers. We want to find the final speed at the top, so let's write down the question mark, what we seek, v final, velocity, there it is, okay? And then we also know the coefficient of kinetic friction, so that's mu k is 0.0800. Again, even if I just write 0.08 or 12 or 60 or 35 or 2.5, I know that they're all 3 significant digits. Okay? All right, so fine. Let's see if we can understand the conservation of energy here. I think that the skier, to start, has only kinetic energy. That's even kind of shown here for us. Only kinetic energy. You can imagine that we can set y initial here, the initial height, to be 0 meters. So the gravitational potential energy is 0. Now let's think. When the skier gets to the top plateau, we would assume the skier still has some kinetic energy, that's kinetic energy final, it's still moving, now has some height, that's gravitational potential energy, but there's more. The skier also had friction acting along the slope. So let's just assume that only when the skier is on the slope, and we'll approximate the slope as an inclined plane, that is the shape of a right triangle, we'll assume that during that period of time that the skier has friction acting, and that's going to be non-conservative work because that's going to be energy transferred into heat. Or if you look at it as non-conservative work, pessimistically, you subtract out work done by friction. So let's write this out. Let's write out our conservation of energy equation. Okay, so the conservation of energy equation here, okay, should be something like the following. It should be the initial kinetic energy, which we said, so that's K initial, capital K initial, is equal to K final, that's the final kinetic energy. Oh, and then hang on, I forgot something. On the left-hand side, indeed, the skier is having kinetic energy, but the friction is taking energy away the whole time. So if we are going to perform this with work done non-conservatively by friction, you could say that's plus the work done that's non-conservative by the force of friction kinetic. We'll come back to that. Okay, then equals the final kinetic energy plus the final gravitational potential energy. Okay, that all looks fine. Let us write out each of these terms. So this is going to be the initial kinetic energy of 1/2 mv initial squared. And let's think about the work done by friction, which is non-conservative. That's going to be, that's going to be work we know to be force times displacement times the cosine of the angle between the force and the displacement. So let's write that out to be plus force of friction kinetic times the displacement. Now the displacement, let's go ahead and call that delta R, because delta R is the traditional sort of displacement variable that we use in this class when it pertains to work, times the cosine of the angle between those two vectors. Now the angle between those two vectors is not going to be theta, it's going to be phi, and phi is going to be the angle between those two vectors. We'll come back to that. This should equal to 1/2 mv final squared, that's the final kinetic energy of the skier, plus mgy final. Okay, so looks like we have most of these variables, m and v initial. We're looking for v final. We always know what g is on Earth, and we know what y final is, but we don't know what phi is, and we don't know what delta r is, and we need to talk about this friction. Okay, so let's do a little aside here on friction. Okay, first of all, we're assuming that the skier is on an inclined plane. Let me type that. So the skier is on an inclined plane. Okay, so we know that on an inclined plane that the force of friction has a very specific form. Force of friction, kinetic, should usually just be force of friction, kinetic, equaling mu k times the normal force. But wait a minute, the normal force on an inclined plane has a very specific form. It's actually in terms of theta. And if you reference earlier in the class Newton's laws, this is actually going to be mg cosine theta. So force of friction kinetic is going to equal to mu k times mg times cosine theta. Then we need to think about this delta r, because now we have something that we can handle in terms of m and theta and g and mu k. Then we need to think about this delta r. So let's go ahead and perform a sketch. And in order to perform the sketch, I will draw a inclined plane, and I'll approximate it as a right triangle. Okay, so let's do that over here. So let's let this be, let's let this be our inclined plane. Okay, I'll move this around very soon. I just want to get the sketch of the inclined plane. Okay, so here's our inclined plane. And let's see if we can grab it and move it. There it is, finally. So there it is. Okay. So then, our inclined plane, we should label certain things about the inclined plane. So, we should label first that y final is the final height on this inclined plane. So that's over here, y final. We're calling this distance delta r. Okay? Delta r is this distance, but furthermore, if we look at the force of friction, now the force of friction has a certain direction, so let's actually get that as a separate color. Okay, so if the force of friction is a vector, the force of friction I think would be in this direction. Whoops, this direction, down the inclined plane. Whoops. Okay, so it'd be down the inclined plane like so. Something like that. So this is the force of friction kinetic vector. But then the delta r has a direction that's up the inclined plane. So delta r is going to be in the direction that's up the inclined plane. So it's going to be like this. Let me draw a nice straight line. There we go. So it's going to be something like that. Now, I've tried to sketch these that you can understand what the direction of the angle phi is. Remember, phi, the way we've defined in this class, is the smallest angle between these two vectors. So this should be the angle phi. And hopefully you realize that phi is exactly equal to 180 degrees. That's the smallest angle between those two vectors. So then we know what the cosine of 180 degrees is from our unit circle memorization or otherwise. That should be -1. And I hope that makes sense to you why it's -1. Because if the displacement is up and the force is down, friction is going to do negative work, because that's where the cosine of 180 degrees comes in. It gives you a minus sign, -1. Finally, also, this delta r can be calculated from theta. So if this is theta, notice that the sine of theta is yf over delta r. So the sine of theta is yf over delta r. So we could solve this for delta r and put this into the expression to get the magnitude of delta r. So delta r is equal to, let's see, y final over sine theta. Okay, so now we have several things to insert. First of all, we have force of friction kinetic, to insert into the problem back here. That is the conservation of energy. Okay, so I think that that's going to go in here, as we show over here. Secondly, delta r is going to be inserted from here. From here. Let's see, I'll do a double underline. So that's going to be the expression that's going to go in here for delta r. And then how about cosine of phi? Well, cosine of phi is going to be just equal to -1. Gosh, I'm having trouble writing here. -1, there we go. All right, so that's what we already said, because it's cosine of 180 degrees. And then, notice that there's going to be m throughout the equation. We'll actually be able to cancel that very soon. And then here's one more thing. Because there's 1/2 in the problem, and we're solving for v final, that's our question mark, I would like to multiply this equation through by 2. And that's because it'll get rid of the 1/2, and there will be no fractions, at least to boot, from coefficient numbers, and then these terms will just have 2's on them. So let's also multiply this equation through by 2. Okay, so let's take this one step at a time. Now, our conservation of energy equation becomes mv initial squared, and then plus, well, the plus actually becomes a minus because it's -1. So let's do minus, because the work done by the force of friction is negative. Force of friction kinetic is mu k mg cosine theta. So that's mu k mg cosine theta. Then delta r becomes yf over sine theta. And then, again, cosine of phi, we took care of the -1 with the minus out front. Oh, and then don't forget, we multiplied the whole equation by 2. So what we should do is we should write this as a subtract -2. -2 at the subtraction. Okay, so this should be a -2. All right. So then that equals to mv final squared. And then there's a 2 that comes in here, plus 2mgy final. Okay, now we're getting somewhere. Next thing is that we see that m, the mass, is in each term in this equation. Okay? So hopefully you realize that the equation then is going to be independent of mass. This is true in a lot of conservation of energy problems. So this mass should cancel out. Okay, so that's an algebra step, dividing out the mass. So we should say independent of mass. That's what canceling out the mass there does. And then also notice we have cosine theta over sine theta. Now earlier in the semester we've talked about sine theta divided by cosine theta is tangent theta. That's a well-known identity from trigonometry class. So cosine theta over sine theta should be the reciprocal of that. So that should be cotangent of theta. So this right here I think will give us a cotangent of theta. And then again we want to solve for v final. So I think we want to move this term over, the 2gy final, with a minus and take a square root to get v final. So let us clean this up and move by moving on to the next page. Okay, so next page, I think we should have this for the conservation of energy equation. We should have, let's see, it's going to be it's going to be v initial squared, and that's going to be minus mu k g, and then instead of cosine theta, it's actually cotangent theta, because cosine and sine went together, times y final. Let's make sure we didn't forget anything on the left-hand side. Oh, we forgot the 2. So it's v initial squared minus 2. So minus 2 mu k g cotan theta y final. Okay. So we need, again, we need a 2 here. Don't forget this 2. And then we've got g cotan theta y final. Okay. And then we bring that other term over, the potential energy term, minus 2 g y final. Okay, so I think that was the term over here on the right hand side. That's this term, yes. And then we've got v final squared, so we need to take a square root. So then we take the square root. That's why I left a little space here. And the square root of all this equals v final. Okay, so let us put the numbers in. Okay, so this is square root of all these numbers. Oops, can't believe he keeps doing that. Okay, so this is going to be v initial squared. So that was 12 meters per second squared. Remember, I'm writing just 12, but we'll use 3 significant digits, minus 2 times mu k, that's 0.08. Again, it actually has 3 significant digits. G is 9.8 meters per second squared, the acceleration due to gravity in free fall on Earth. Cotangent of theta, that's going to be cotangent of 35 degrees. Then we have y final. Y final was 2.5 meters. And then we have minus 2g, minus 2 times 9.8 meters per second squared times y final 2.5 meters. Okay, and then let me finish extending this square root. Okay. All right then, and that's equal to v final. Okay. So what you should do is you should work all that out in your calculator. Okay? Now, by the way, in your calculator, when you do cotangent of 35 degrees, just do 1 over tangent of 35 degrees. Most calculators don't have a cotangent button. But when you work all that out, I hope you should get a v final of approximately 9.46 meters per second for the final velocity. Okay. And let's go ahead and see if this seems to make sense. Again, no idea why. That's stupid. Okay. So let's go back to the original problem. So the original problem had the skier with an initial kinetic energy. The work that's done by friction takes energy away, so the final kinetic energy, thus the final speed, should be smaller, but also the gravitational potential energy takes energy away. So that makes it also less in terms of the gravitational potential energy, because gravity does negative work in this case. So we're storing up gravitational potential energy. So we expect that the final velocity is certainly less. Okay, so there it is. Thank you very much for your attention. I know this was a long problem, a lot to keep track of, but hopefully I took my time and I explained it carefully. Please smash that like button and subscribe to the channel, and I will see you in the next video.